Hey, folks, good morning, good afternoon, good evening, wherever you are in the world watching us live today. It's going to be a fantastic talk by my colleague Alan Caldera here. So, just for quick introductions, my name is Amey Banarse. I lead the solutions engineering team here at Yugabyte, and it's been a fantastic journey for the last 5 years. And with me, I have a pleasure to introduce today to you all Alan Caldera, who is the distinguished engineer and field CTO at Yugabyte. Again, having been spent more than 5 years here at Yugabyte and a vast amount of experience in relational database industries, all the way back from Informix, then working on Postgres, DB2, analytics, and now finally distributed SQL databases and modernizing our customers' environments with Yugabyte as well. So with that, Alan, I'm going to hand it over to you. Please introduce today's topic. We have an exciting set of crowd here logged in live. So please go ahead and kick it off. Thank you.
Okay. Thanks a lot, Amey. Okay, today's talk, we're going to talk about YugabyteDB's YCQL versus Cassandra. So I wanted to start with a couple of notes about who we are and what we are. So Yugabyte was founded on the belief that the next decade will see a major change in the systems of record that enterprises use to run their businesses and offer digital services. We are the company behind YugabyteDB, a distributed database, SQL database built first and foremost for transactional applications and to support enterprises as they move to cloud-native digital-led world. The database is 100% open source and designed to run on any cloud, private, public, hybrid, multi-cloud. The flexibility and openness are essential to our customers and position us uniquely in the distributed SQL market. YugabyteDB is used by both small companies and Fortune 500 alike, retailers, advertisers, financial services, telecoms, and many others. The second question I wanted, people ask me is, okay, well, where does the name Yugabyte come from? So Yugabyte is a play on words. Basically, it's the beginning of the word yuga is derived from the Sanskrit word for epic or era. So this denotes that this is basically data that lives for a long time. And then byte is a play on, we have these various names out in convention like, zettabyte, petabyte, exabyte, and there's another one called yottabyte, but that's not what we are. So we're basically, the name Yugabyte is basically data that lives forever at scale. So the other thing that people say, well, why should we believe you when we talk about Apache Cassandra? Apache Cassandra has been out for a number of years, and so there are a number of players out in the case space, in the key value space, things like DataStax and Scylla and Amazon Key Spaces. So we are actually the company in terms of the people here actually built Cassandra at Facebook and open sourced it, before a lot of people saw it out in the whole wide world. So this is our DNA is Cassandra. And so who better to take it to the next level than YugabyteDB? So I want to give you kind of an overview of our architecture. So basically, Yugabyte has a multi-layered architecture where at the front end we have this extensible query layer that provides what we call shims, and these shims are for basically plugging in things like our Postgres compatible API as well as our Cassandra compatible API, and in the future we may go to others like Graph or MySQL or something else like that. It's also important to note that while DataStax and Apache Cassandra call CQL Cassandra query language, that is not what YCQL actually is. It would be kind of weird to say Yugabyte Cassandra query language. So actually, technically, it's called Yugabyte Cloud Query Language. So keep that in mind. That we're not saying we are CQL. We are CQL inspired. Down below the actual query layer is our document DB storage layer. So this is what actually provides all of the replication, load balancing, distributed transactions, and sharding to basically allow you to scale Yugabyte to petabytes of storage and hundreds and maybe even someday thousands of nodes. Below that is basically our management platform that says, okay, well, where am I going to put it? I'm going to put it on AWS. I'm going to put it on Google Cloud, Azure. I'm going to put it in Kubernetes. I'm going to have on-premise or some combination of those. So basically what you look at this is as a unified database that drives success across many different use cases. So we all know about Yugabyte YSQL. We've done a number of talks around our Postgres capabilities, but today not many people know about this Cassandra inspired API. And so we have a number of use cases on this, a lot of them being things like systems of record for things like product catalogs and IoT data, as well as serving layers for that data that allow enterprises to serve point consistency queries that say, okay, this is the state of this record, and we don't have the problems of eventual consistency when people make updates, and you have to wait for things to be reconciled. So in our query layer, we offer a number of additional enhancements on top of what you've come to love about Apache Cassandra. So the first thing and most important is, we do provide faster reads. Well, how do we provide faster reads? Well, the very simple breaks down to the fact that you only have to make one of those reads. In Cassandra, you actually have to make at least 3 reads to basically say, okay, well, which copy actually is right, and then it votes to say, okay, well, these two things think this is the right answer, so here it is. So we're saving you those extra sets of reads in order to give you the definitive answer of where it is. On top of that, we add things we call read replicas, which are basically nodes that serve additional copies that are actually eventual consistent from a read perspective, but not from a write perspective. So we basically this allows you to get data that's closer to your customers without sacrificing sacrificing consistency. So to add to that, we also add strongly consistent secondary indexes, and we'll go more into indexings here in a little bit. So in order to support those, we have to have things like distributed ACID transactions, and we also have to take care of things like going across multiple regions.
So Alan, just quick question. Given the fact that we have a lot of Cassandra professionals here today, let's help them compare and contrast their existing world in Cassandra versus how their life would be if they use YugabyteDB's Cassandra API as well. So let's go deep dive into that, make our audience happy with it.
Yeah, okay. So the great thing is that because we are inspired by the same API, there's not much work in actually making that transition from Apache Cassandra to YugabyteDB. A lot of the same structures work right out of the box in terms of your application and things of that nature. But what you'll see right off the bat is much better performance from a write perspective as well as a read perspective. And then where we layer some of these other things in, with our enhancements around things like JsonB, where you can basically have, more document-oriented type workloads. This allows you to basically enhance the experience for your customers and delight your developers by not having to write additional code to say, okay, well, I have all these different tables that I have to, maintain and manage, from an application point of view. I can now just write things to a single table. Operationally, you look at the density of nodes in Cassandra today, and typically a Cassandra node is, at most maybe 2 or 3 terabytes at most. We've actually tested this at scale many years ago, where we were actually able to go in excess of 25 terabytes per node. And that 25 terabytes was compressed. Okay, so we apply compression to our data. So really the compression, if I remember right, was somewhere around 3.5 or 4 to 1 in that data. So really we were managing close to 100 terabytes, so equivalent to 50 nodes of Cassandra on one node. So this allows you to really save on your infrastructure and your management, and you don't have nasty things like no tool repair or worrying about Java GC weights because we're written in C++ versus having to go through and tune Java JVMs. So let's talk about some of the additional things. So we've kind of started to brush on this, that the index implementation is very different between Cassandra and YugabyteDB. So Cassandra implements indexes at basically a local level. So on the individual nodes, they can actually say, okay, here's this index, but if I want to read that on a different node, I may not have that record in the index at all. So it's kind of hit and miss. So Yugabyte does it with strong consistency. So as part of the transaction, so when you write to the table, the index is automatically updated, and your developers do not have to go and basically maintain these basically user created indexes by writing additional tables that change how things are partitioned and clustered. The other big difference here is that Cassandra is it's generally configured to quorum, where you have to do those additional reads and writes to get strong consistency. And so this is what we do right out of the box. So Cassandra actually allows you to tune write consistency as well, so that you can say, okay, well, I want to just write one copy and go on. But later on, you might find that, okay, well, it didn't make it all the places it needed to make it, so now I have to go in and run node tool repair to basically fix everything that went wrong earlier. But there's none of that with YugabyteDB. And then I mentioned JsonB, where basically we can say, okay, well, now we have these Mongo-like document workloads where you're saying, okay, well, I just want to be able to refer to a JSON document and be able to pull information out. Now, you're probably wondering, well, why did you all put it, how does JsonB fit into this whole key value model? Well, in our storage engine, JsonB is just yet another key. So, you imagine a JSON document has, you have the key of the row, and then you have the column that's the actual value. Well, the value actually points to set of attributes or arrays of attributes that are further basically additions on the end of the key to get you down to a specific value at the attribute level. So we're able to, to store this very efficiently. And as you'll see later, it's quite a delight to actually go in and update.
Yep.
So I wanted to talk a little bit about how we store things. So, basically we have, there's the old, talk about tablets versus partitions. So while we are both log structured merge, Cassandra actually has a limit of 2 billion cells per partition, and they generally, suggest that you size the partitions to be, anywhere from 10 to 100 megabytes, or maybe a little bit more. Whereas tablets in Yugabyte really have no limits on sizes. I've seen small tablets that are, in the hundreds of meg to gigabytes to even terabytes in a single tablet. Now, is that a great idea? No, it's not a great idea, but it happens. But we don't force customers to actually go in. It's basically their choice whether they wanted to deal with it by, going and splitting up the tablet or not. And this is what allows us to, get that scalability a lot quicker. As you know, that Cassandra, when you actually scale it out, Cassandra actually has to go a whole node at a time, whereas in Yugabyte we go a tablet at a time. And so this allows us to scale a lot more quickly and make use of new hardware. So I'm going to skip over this. Okay, so let me go to talk a little bit about indexes a little bit further. So we're all familiar with Cassandra. You specify a primary key so that you have, partitioning key, partitioning columns and clustering columns, and that's pretty much about it. If you want to, represent the data a different way with a different clustering key, the same data a different way, whether it's partitioned differently or clustering differently, you actually have to create additional tables and maintain that consistency in your application. With Yugabyte secondary indexes, we can actually create these indexes such that, based on, that single write, you can say, okay, well, I want it to partition by column 1 here and clustered on column 2 and column 4, but I can have an index that is partitioned on column 5, and then I could be, ordered by, column 1 and column 4, so that you don't have to continually go and change your data model as you go along. And all of these are globally as consistent. So how do they work? So basically, indexes are basically, implemented as tables. So tables with tablets, and so they can scale. They can scale out as the amount of data grows. You can have additional. You can have multiple indexes per table. I've had some data models that have had, as many as 13, 14, 15 indexes. And really you're probably thinking, well, why, wouldn't that be really expensive? Well, yes, as soon as you create an index and actually, have to maintain it, that first act is actually pretty expensive because it becomes a distributed transaction rather than a PK update. But each additional index actually is a very small upcharge from that point. Okay. So the create index statement looks like most SQL languages. The difference here is that and this is important to note, that tables, in order to be indexed, have to have transactions enabled. So basically, you're saying, okay, I may put an index on this table at some point. So I'm going to go ahead and enable transactions. There's actually no cost to actually doing this. It just gives you a way of saying, okay, well, I might put an index on, so I'll leave it open. If you create it non-transactional, in other words, you leave off the transactions enabled clause, then basically it's the table has to be recreated with transactions in order to add indexes later, or you must add do a user enforced index otherwise. We've also to kind of help determine what if indexes are being used. We've also added an explain plan like you're used to using in YSQL and other SQL-based products, so that we can actually show you what query plan we're actually using to retrieve your data. So the other nice thing is we can add things like covering indexes, where we have an include syntax. So basically, you can add on additional columns so that you can do what we call an index only scan. So you add in these additional attributes such that the column, all the columns that you want to retrieve in a particular query are located in that index table, so that you're only doing a single read and you're avoiding access to the primary table.
Yeah. So Alan, this is pretty handy when it comes to IoT style use case where you're not doing multiple reads all the time, and you can get it in one single. Very performant, right?
Yes, extremely performant. You can do a lot of very powerful type workloads, and be able to really take advantage of instead of having to maintain multiple tables, it's all about having maybe one or two central tables, and then basically everything else becomes an index, whether it's using covered indexes, regular indexes, or even additionally, we can support unique indexes, so multiple unique indexes in addition to the primary key, to give you some additional data validation in your schema, as well as partial indexes. And you're probably going, whoa, okay, so partial indexes, I can actually say now, let's say that I had, some kind of hierarchical model like you would see in a product catalog. So I might have SKUs and products and collections are basically collections of products. Products are, combination of SKUs. And so I can basically cut down, one of the ways to cut down the number of indexes that are actually written is to make it a partial index, so that you say, okay, well, this particular record is part of this entity, so I'm only going to write it by using a partial index when this particular attribute is set.
That's fantastic.
Very
Yeah, this can help us with a lot of the enhancements. So Alan, yeah, for our audience, they were very curious about JsonB. So maybe let's spend a quick few minutes.
Yeah, so that's the last topic we have here. So JsonB. So we're able to, this allows you to, give it basically. We took this from Postgres. That's why it's called JsonB. So basically, it's attribute ordered JSON document, so that we can do an efficient binary search. Because as I said, all of these become keys. So we can actually say, okay, now JsonB does not require that you add transactions. This particular example says, okay, well, I happen to have transactions enabled because I might put an index on those attributes. Yes, I can even do that like I do in Postgres. So I'll show you an example here. So I'm going to insert a couple of records here. And so I have, varying, a couple of records here with some attributes. And I've even included some arrays. When I actually go to query, there are a couple of different operators. The first, dash single arrow, basically says, okay, I'm referencing another JSON, and then a dash with a double arrow basically says, okay, I want this to this is my actual text value that I want to retrieve. So in this example here, I could actually say, I want to pull out in this order detail, I want to pull out a column and actually create an index on it if I like to, if I want to. So let me show you an example. So in this example, I'm saying, okay, let me select an order where the product, the product going to a specific customer is jim@gmail.com. Well, when you do that, when you run that query, it's going to do a sequential scan because it's got to look through each and every record. Well, that's not going to be very performant. But with the power of YugabyteDB, I can say, okay, I'm going to create an index on this particular field in the JSON document and include the order ID. So now when I say, okay, I want to find out which orders have this particular customer email associated with them, I can do this index-only scan to actually retrieve that specific record. And finally, this is like my favorite feature of JsonB within YCQL. This is really unique, even from our even from YSQL's implementation, is that you can actually create JSONs without actually having to create a JSON within your application. So if you're getting the data as, little bits of data from different parts of a form or different feed, you can actually say, okay, I'm going to update. I can use the update statement to actually create the JSON as I'm going along. So it will basically keep adding to it as it continues to run, so that I don't have to collect all of the attributes and then write a huge JSON. This allows us to also update individual values, and it's really a joy. And we've extended this into our Spark connector as well. So that's this is an example of that, where you can just say, I'm going to put update these things in different statements, and these could be at different times. It'll just go ahead and add it on to that.
So, Alan, given the fact that these features are very similar to a document database that most of our audience would be have an experience compared to a MongoDB or a DocumentDB or from Amazon or a few others, is the JSONB the same implementation, or is it a different implementation? Can you?
It's a slightly different implementation. So it's not a some of the things like Mongo, actually it's like a BSON, so it's a binary JSON, and really ours is not really like that. It's actually, you just think about it as we're just doing a sort on the attributes themselves. So you don't have to put them in sorted order. We'll take care of that, because underneath it is something that is a storage engine that knows how to sort things. So
exactly.
makes it very powerful.
Right. So, and Alan, for our Cassandra audience here, when you compare Yugabyte's JsonB feature versus what open source Apache Cassandra provides, what are your thoughts on that?
Regular Apache Cassandra, typically it's all stored as just plain old text. Correct. So you're just basically saying, okay, I've got a text blob here that's got JSON in it. Okay, and you can, I believe there is a function that allows you to actually cast a result set out as a JSON for consumption by an application, and we support that syntax as well. But we add to the power of this by being able to actually manage the JSON efficiently within the database, so that you can query on it and pull out the attributes that you need without having to incur a large cost in retrieving a fairly large document.
That's very great, Alan. Thank you. So for the audience here, again, you folks can go ahead and start using Yugabyte. It's fully open source, and just observe it for yourself what value add-on you'll get compared to your Cassandra data models and query tunings in general. Now, most importantly, we have done this for a lot of Fortune 500s and Global 2000s already. Like, we have helped them modernize their old school or legacy NoSQL applications, which needed transactional consistency, transaction and strong consistency with Yugabyte's YCQL API. And some of these success stories are available on our website, so please go ahead and see them as well. And whenever needed, you can join our community Slack channel, yugabyte.com/Slack, and start asking these questions. We are happy to come in and help you with your data modeling, query tuning. If you have any questions when it comes to like porting over your Cassandra code to Yugabyte YCQL, we'll absolutely come in and help you and set a time with you as well.
Yeah.
So with that, Alan, thank you for enlightening us with all the Cassandra knowledge that you had in only 20 minutes. Love to see you doing these a lot more to help out our audience as well. Prem, thank you again, being a fantastic host and leading the YFTT series. All have a nice day. Thank you again.